Okay, so today we're gonna change gears a little bit and start, in general talking about operads. Yeah, so today I won't mention what an operad is. I'll tell you what a monad is, and then Thursday I'll tell you how to get a monad out of an operad. If someone has a other preferred pronunciation, like if you're really sure it's monad, tell me. Okay. Also, I'm not sure if it's a made-up math word or if it's a real word. Okay, Michael's heard both, so I think I normally say monad. Yeah, so I'll define monads. We'll talk about examples. Oh, it's a real word. Okay, and yeah, so we'll talk about examples like the free group functor, loop space, functor, little cubes. So some of these will come from operads and some of them won't. We'll talk about that next time, and then we'll talk about algebras over monads. Yeah, so eventually the idea is that monads, or more specifically operads, will parameterize certain kinds of algebraic structures, and the algebras will be like the algebraic structures. I don't know, that wasn't said well. And since we're sort of starting over, if you lost the thread, hopefully you'll be able to start following. On the other hand, this is kind of abstract, so feel free to stop me and be like, what does that actually mean? You just said natural transformation 6 times, but like concretely, what are we talking about? Feel free to say things like that. Okay, so I guess I ruined the punchline. Last time when we were having technical difficulties with next talk. Yeah, so a monad is a monoid object in the category of endofunctors. So what does that actually mean? So let C be a category. So a monad is a functor M from C to C. So endofunctors means, functors from a category to itself. Eventually C will be like spaces or topological spaces or vector spaces or chain complexes or something. And so, being a monoid object basically means it has multiplication in a unit. So a unit in this context is a natural transformation from the identity functor to M. And the multiplication is a natural transformation from M composed with M to M, and then they satisfy these unit and associativity axioms that I'll talk about. I guess concretely what this is saying is that for each object X, you're going to have a map from M of X. So like X is an object, M is a functor. So Mx is an object. You can apply M again. So M of X is a object. And then you get a map to X. So you think of it as like you're combining these two terms. Okay. Yeah, and like, I guess the reason why these memes exist, like I didn't make them, we talked about this last time, was that apparently this is like something that appears in functional programming, and this definition of being a monoid object in the category of endofunctors, I think eventually is a useful way of thinking about it for mathematicians, but maybe is intimidating for computer scientists. Yes. Okay. So then I believe, my guess is that the computer scientist made this meme. My goal is to describe this joke, like explain this joke enough that it's, as not funny as possible. Okay, so what is associativity? So it's like you have M, X, And there are two different ways of getting to mx. You can, you can combine these two m's, or you can combine these two m's, and then you use the multiplication, and you get to mx. And the statement is that this associativity is the statement that this diagram commutes. So you combine these two terms, or you apply the natural transformation to this composition of functors or to that composition of functors, and it'll end up being the same. And the unit is similar diagram. You can put the identity on the left or the identity on the right, and then multiply, and you should get the identity. Sorry, you could put the unit natural transformation on the left or the right, and then if you multiply, that's the same thing, and it's the same as just the identity functor. Sorry, identity natural transformation from m to m. Also, if anyone wants to stop me and just say I don't know what a natural transformation is, or I don't know what a functor is, feel free to say things like that. Okay, so let's try to make this more concrete. So what's an example? So we'll let C. So everything has this underlying category. So C will just be the category of sets. And we'll let M from C to C be the free abelian group functor. So M is going to take a set and send it to the free abelian group on that set. But then we're going to view this object just as a set. We're going to forget that it's an abelian group. Okay, so what do we want? We want this map M. We want a natural transformation from M composed with itself to M. So what does that mean? That means for each object, we need a map from the free abelian group on the free abelian group on the set to the free abelian group on the set. And concretely, so what's an element of the free abelian group on the free abelian group on a set? Well, it's a formal sum of formal sums of elements in S. And you can just view that as a formal sum of elements in S. Anyone want, any questions? Okay. Yeah, so any guesses at what the identity should be? So given a set S, so we need a map of sets from S to Z adjoin S.
Just a formal sum with one term?
Yeah, so just lowercase s goes to, 1 times lowercase s. That's the unit of the monad. And then you could check, that this multiplication map and the unit satisfy all of satisfy the two axioms from the previous slides. Okay, and you can do, so you check that this diagram commutes. This is formal sums of formal sums of formal sums of elements in S. And if you basically merge these two formal sums or merge those two formal sums and then merge what remains, you get the same thing. And similarly, there's a unit condition. Okay, and you can do the same thing. It doesn't need to be abelian. You can do the same thing for the free group functor. You send S to the free group on the set S. So this is my notation for the group with generators S and no relations. And what's multiplication? Multiplication is you have a formal product of elements in S. You have a formal product of formal products of elements in S, and you just multiply everything. I guess I should have been careful about order, but you know, I guess the way I wrote it isn't clear what the order is, but if you write it down, it will be clear what the order should be on this product. Okay, so here's some maybe more topological definition. So or topological example. So let's C be category of base topological spaces, and we'll let M apply to, I guess, I don't know, I'll just cross this out. We'll let M be the functor loop suspension. So M of X, you know, is loops suspension X. So X is the base point, you know, because suspension and loops, at least loops depends on a base point. Depending on your model of suspension, it either does or doesn't. Oh yeah, so one thing you'll notice is like this functor is built out of an adjoint pair of functors. There's a sense in which all monads are. I've never found that particularly helpful to me, so I'm not going to emphasize it, but it's not a coincidence. Yeah. Okay. So this multiplication map is a natural transformation from loop suspension to loops suspension. So remember that the data of a map from X to loops Y, tell me if I've gotten this wrong, is the same data as a map from suspension X to Y. So so what we want, my handwriting isn't good enough. Okay, we want a map omega sigma X goes to omega sigma X. Well, by this adjointness, that's the same as a map sigma omega sigma X. You know, it's the same data as a map sigma omega sigma X. And then you just, you know, we have a preferred map like this, just the identity. So this multiplication is just going to be the adjoint of the identity map. And again, similarly, adjointness, you know, the unit corresponds to a map from X into omega sigma X, but that's the same data as a map sigma X goes to sigma X. So you just take the identity here. Yeah. Yeah. If you want to think sort of more concretely, what is this? This is saying like that X goes to F from, you know, S1 into S1 smash X. And the formula is that, like, maybe I'll say X, little x maps to a function. And that function, maybe I'll call this f sub x. F sub x of t, well, it should be a point in the S1 smash x. So we need a circle coordinate and a x coordinate. Well, you just send it to like x, the t smash x, because we exactly have a circle coordinate and a x coordinate. Any questions or requests to repeat something, or just someone want to express that they don't like categories or something? But you could sort of see that I kept just saying blah is the adjoint to the identity. So whenever you compose a functor with its adjoint, you can build one of these monads. Okay. So, oh, I just wrote this out on the previous slide. Yeah. So concretely, what we want is oh, this is like the definition of multiplication. So if you have an element of loop suspension X, we want to multiply it and get an element of loop suspension X. So, what is that? Well, we have this based map from a circle into a circle smash loop suspension X. That's what F is. And F of T is going to be so this data, I guess, is the data of some point in the circle, S sub T, and some function G of T, where G of T, is in here. So it's a function from S1 into suspension of X. And then we want an element here. So this should be a function. And you compose. Okay. So here's another example of a monad. So recall from when we were defining like product structures and homotopy groups, that C and K is the space of little k cubes in an n cube. So this is the space of embeddings of so the n cube is just I to the n, and it's the embedding of the disjoint union of k copies of this into I, which are compositions of translations and like coordinate. I guess in my pictures they're always squares. Up to homotopy doesn't matter. Let's just say axis, or let's just say scalings. And the A is a typo, it should be and. Whatever. If you want, you can have rectangles. I don't care. Each of you can decide for yourself if you want rectangles or you only want squares. Yeah, so because we're assuming they're compositions of translations and scalings, it's a function is entirely determined by its image, and its image will be some picture like this. Yeah, and so each of these functions is like I different embeddings, and they all have disjoint images. And I don't care if, let's say, they overlap at the boundary. It won't matter. Okay, so here is a functor. It's kind of from topological spaces. Oh, there's a question. The audio is bad. Is it an internet problem on my end, or? Okay, so audio is fine for some people. Also, like periodically I lean down. I don't know if that's, I'll try not to do that. Yeah, but feel free to just interrupt me and say, like, repeat it if you are having internet problems. Okay, so yeah, so what do? You send, this is a functor from topological spaces to topological spaces. You send a space X to this disjoint union over K of configurations of the space of K cubes cross over the symmetric group with X to the K. So, how should you think about this? You should think about this as now it's the space of it's the space of cubes, but each cube is labeled by a point in X. So if like X, Y, Z are in X, then the cubes are labeled by X, Y, and Z. So in this page, the cubes are ordered like 1, 2, 3. These are distinct integers. Here, they're labeled by an element of a space, and there's nothing preventing X from being equal to Y. And so we don't have a first cube or a second cube. we just have cubes and they happen to be labeled by points in X. And, you know, we're using the topology on X. So if like this, like lowercase y can move to a nearby point in a continuous way. And the, you know, the space of cubes has a natural topology, like the cubes can rotate and the labels can change. Yeah, so the claim is that this is going to be a monad. You send a space to the space of cubes with labels in that space. And we're disjoint unioning over K. So this is, you know, kind of arbitrarily many cubes. And they're not ordered, but they're labeled by X. Yeah, so we need a natural transformation. So we need a map like this. So what's an element? What does an element of cubes X look like? Any guesses? Like, how should I draw a picture of this? Yeah, so it's cubes in cubes. Yeah, so like cubes X, this is cubes labeled in X. This is cubes labeled in cubes labeled in X. So what we need to do is we need to take a picture of cubes labeled by points in X and map it to just cubes in X. So yeah, so like given this picture of cubes labeled by points in X, how do we get a picture of just cubes labeled in X? How do I not say cubes twice? Yeah, you just remove the middle. You remove the middle cubes. Let's see what the picture is. Yeah, so if you just, you know, you just cross out the middle cubes, erase them, and then you get cubes in cubes labeled in X. So if you have cubes labeled in cubes in X, you can just erase the I guess it depends if you count the big cube as a cube. I was going to say the outer cube, but maybe I should say middle cubes because it's like there are 3 layers. Yeah. And then, you know, what's the unit? So we need a map from X into CNX. Any guesses here? So like given a point in X, what's your favorite, you know, how do you assign to that a cube with labels in X? Preferably someone other than Zach or Michael should answer this. Or like say I should slow down or repeat something. Yeah, so like, I don't know. So, you know, we have this point X. You know, maybe we want to send it to that. That's probably a bad idea. Anyone have a better idea of what cube we should send this to? Yeah, so
one big cube, like the whole thing, maybe.
Yeah. So the most natural thing you can do is you just send X. I guess I have a picture. you just send x to the identity embedding. So it should be a cube labeled. It should be a little cube and a big cube, but you can just take the identity map, so like the biggest cube possible, and then you just label that with x. So this is the analog, here, we said take some element in S and send it to 1 times S. You should maybe think of this big cube. This big cube is 1, and this is like 1 times X. Yeah, let's see what's. Oh yeah, and then you can check that these operations are associative, and that this is a unit. Okay. Any other questions before we move on to algebras? Okay. So like an algebra is an object of the category and a map from the monad applied to the algebra to the algebra. So I guess this is an algebra. Wait. This sentence, I should have actually read the sentence. Probably I'm missing like is called an algebra. Is called an algebra. This phrase should be somewhere in the sentence. Yeah. So what am I saying? So an algebra is something such that is an object such that you have a map from MA to A, and you have an inclusion, so you have a map from MA to A, making these diagrams commute. So basically, you maybe if you're thinking that like M is like a group, then this is like a group action. So like A is something with a group action. That's maybe not the most useful perspective, but it is analogous to that. So what this is saying is basically if you multiply things in A by the unit, you get the identity on A, and we have some associativity involving this product and the multiplication in A. So like you can either maybe if you think of this as MA, there are 2 things you can do. You can combine the 2 M's, or you can combine the M and the A. That lands you in MA in 2 different ways. And then once you're in MA, you just multiply and you get to A. And the statement is that those 2 things are going to be the same. Okay, let's see what happens in examples. So so the proposition is going to be that an algebra over the free abelian group functor, the data of being an M algebra when M is the free abelian group functor is the same information as being an abelian group. So this is the sense in which monads encode algebraic structures. So this functor from sets to sets encodes the information of abelian groups. So so suppose A is an abelian group, and we have a formal sum of elements in A, so that's an element of Z of A. Well, the algebra structure map should give us an element of A. So how do you take a formal sum of elements in A and produce an element in A if A comes with a structure or an abelian group?
Perform the group operation.
Yeah, just perform the group operation. What did I write? Oh yeah, it's hard to write down in formulas, but it's like here I'm thinking of this as a formal sum, and here I'm thinking of this as just an actual sum. Like use that it's an abelian group. So add A to itself ni times, and then add all those up as I varies. Yeah, and algebras over the free group functor or just groups. So let's say that now let's say M is the free, is n of S. What is the standard, where, with the standard monad structure on that functor? Any guesses for what M algebras should be?
Just monoids, commutative monoids.
Yeah, just abelian monoids. Yeah, abelian monoids. Yeah, I think if I'd said the free, if I said the free monoid, then it would be monoids. So basically, all monads are. I mean, you can think of a monad. I guess that's the next slide, but at some point the slide will appear. But you can think of monads as free M algebra functors. I guess composed with a forgetful functor to the underlying category. And then, so if your functor is like a free something algebra functor, then algebras over the monad, that monad will be something algebras. Yeah. So, okay. So like if let's say R is a ring and let Lie be the free Lie algebra functor, I don't know what that, I don't know how to write down a formula for that. Maybe I do, but Lie is a monad and Lie algebras or Lie algebras is the where you parse this as saying algebras over this Lie monad are Lie algebras in the classical sense. You can replace Lie with whatever you want. And so maybe this is slightly more surprising. So if you look at this loop suspension example, then loop suspension algebras are just loop spaces. So, in some sense, it's saying you should think of loop suspension X as the free loop space. And you might be wondering a little bit like, what is the suspension doing? And I don't know that I have there's probably a correct answer, but I don't know what the correct answer is. Yeah, so we're going to prove like a harder theorem than this that will imply this, or the proof will imply this, but let's just talk about the easy direction. So this theorem says like the information of being an algebra over this monad is the same as if you're an algebra over this monad, then you are a loop space and vice versa. And if you were to write down a category of algebras over this monad and a category of loop spaces, if you were to do that in the most natural way, then the categories would be equivalent, etc. Okay, so let's just talk about the easy direction. So I'll just let's say A is loops Y. I need to build this map from loop suspension A to A. So from loop suspension loops Y to loops Y. Typo. Oh yeah. Oh no, it's not a typo. So if we can construct a map like this from suspension loops Y, you can just apply the loops functor and then you'll get the map we want. So this is what we want to construct. But then we'll just take this to be the adjoint of the identity. And concretely, what is this saying? It's like, oh yeah, so a point in here is like a coordinate in the circle and a loop, F. So T is a point in this, is the suspension coordinate, is the point in the circle, and F is an element of loops Y. And so what is this map? Well, we just want an element of Y, so you just compose F with T. Yeah. And the harder direction is that if you have an algebra, maybe it's obvious, maybe it's not. I know a proof of it, and the proof I know isn't obvious or isn't super obvious. If someone sees a super obvious proof the other way, like blah, 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 adjoint to the identity functor, blah, 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 feel free to interrupt and we'll talk about it. Like, if you are a algebra over this monad, why are you the loop space of something? I don't know. It's true. I don't know if it's obvious. Oh yeah, so this is this comment that I made before. So if M is a monad and X is an object, then, well, first of all, MX is naturally an M algebra. Yeah, so like, why is that? Well, we need a map. So, you know, if A is MX, well, we need a map from MA to A. But that's exactly a map from M of X into MX. And because M is a monad, we can merge these two, you know, we can just merge these two factors. Any questions? Okay, so, you know, the next comment is that the data of a map from, let's say A is an M algebra, the data of a map from X to A is the same data as a map of M algebras from MX to A. Yeah, so this is like a universal, maybe this you should think of as a universal mapping property that, I don't like that color. You know, so there's a map from X into MX, and let's say you have a map in the underlying category from X to, you know, so F is a map, is just a map in C. Then we're saying then there's a unique map, I don't know, F hat. And F hat is a map of M algebras. So this is the usual universal mapping property for a free thing. So we're just going to call MX the free M algebra on X. And, you know, the justification for this name is the second proposition. Yeah, so this sort of, okay. So I don't know if this is actually true. Maybe Michael will want to disagree with me. Feel free, you know, or anyone else. In my opinion, 95% of the reason to care about operads is or to care about monads is this example of the little cubes. So let's sort of talk about algebra, little cubes algebras. Or yeah, so I guess the remainder of the class is going to be examples of algebras over the little cubes monad. So here's a list of sort of interesting ones, or things that I consider interesting. Well, free algebras, okay, that would be true for any monad. Configurations of points in the cube are going to be a algebra, is going to be a CN algebra. N-fold loop spaces are going to be CN algebras. Abelian monoids are going to be algebras. Monoids when n is 1. So if we look at one-dimensional little cubes, the space of holomorphic maps, based holomorphic maps from CP1 to CP1 is going to be an example of a C2 algebra. And you know, maybe another example that I don't have a slide for, but a CM algebra is a CN algebra as long as M is bigger than N. So you should think of this as sort of analogous to if you have a abelian group, it's a group. So like there's a sense in which CN measures commutativity, and as n goes up, you become more and more commutative. And when n is like infinity, you become commutative up to homotopy, which is different than being strictly commutative. Okay, so like, you know, if you're CM, you're like have m degrees of commutativity. So in particular, you have n degrees of commutativity if n is less than n. Yeah, so let's talk about cubes and configuration spaces. So in terms of objects we've considered before, what's the homotopy type of CNK? So this is the space of k n-dimensional cubes in a n-dimensional cube. Or I guess this is a space of embeddings of disjoint union of k copies. Maybe I'll go back. Yeah, so picture. Oops. Yeah, so yeah, any guesses for the homotopy type of the space of these things in terms of objects we've considered before? So up to homotopy doesn't matter how big these cubes are. This is like a leading question, so you should it's a guess. Yeah. So
you mean?
Sorry.
You mean think of them as points?
Yeah, you can just think of them as points. So up to homotopy, the only thing that matters is like the center of mass and like the order. So you can think of this the space of cubes as just it's up to homotopy. It's just a configuration space. Here's my slide. Yeah. So this is just the homotopy type of the ordered configuration space of k points in Rn. So the cubes are ordered, but and they have sizes, but the how big the cube is is like a contractible amount of data. So up to homotopy, it's just like where are the centers of the cubes in the order. So it's equivalent to this configuration space. There are people that study spaces of like hard disks or cubes where the cubes have like a fixed radius, and then it's not homotopy equivalent to configuration space. I don't know. I don't think about this at all. This is more like actual geometry, but like if you have cubes in a disk of radius. Sorry, if you have balls or disks in a disk of radius 1, let's say they're unordered. Let's draw a picture for no reason. Like once the balls become small enough, the space of balls in this ball is connected. But if the balls are kind of big, they can get like snookered, I think is the correct word. It's like in pool when things become like obstructed. You can like wedge them in so they like can't get out. So like this connected component, this point, and this point might be in a different connected component. I don't know. Someone told me this. But like they also were involved in a recreational fist fight, so I don't know if you should trust this person. Okay. Yeah, but here, here we allow the sizes of the cubes to vary so they can't get snookered. Whatever the word is. Yeah, so what's the homotopy type of, let's say, this, the monad built out of this evaluated on a point? Any guesses for this one? I'll call on Zach in like 30 seconds, unless someone has a... like The first thing was ordered configurations. What's the next obvious guess? Ordered configurations. Okay. So yeah, so if you have the homotopy type of, so this is cubes labeled by a point. So the labels don't, the labels don't matter because, or the label, I guess, there's no information in the labels. So all of the cubes have to be labeled by point. So here we're taking X to be, by point I mean like a 1-point topological space. Yeah, so now we're looking at the, the only information is like the center of mass of the cubes, like the size of the cubes don't matter, and the labels are just a point. And I guess we're disjoint unioning over K. So here it was like these two Ks were equal, but there's no K here. We're just unioning over all. So this cubes monad applied to a point is going to be equivalent to the this unordered configuration space of points in I. And when I don't have a subscript, I mean union over all numbers of points. Any questions? Okay. Yeah. So now, I guess I claim that this is configurations of points in a cube is in CN algebra, and the so I need to tell you what the structure map is. So here we have cubes. We have a cube labeled by cubes. Or sorry, I guess we have cubes in a cube, and the cubes are labeled by points. I think I said cubes the correct number of times. And what do? Basically what Michael said earlier, you just delete the cubes, and now you have now you just have points in the cube. So this is the algebra structure map. Okay. Oh yeah. Any questions about this before I move on to loop spaces? Yeah, and you can do this with any kind of label you want. So instead of configuration spaces, you can take them with labels in a partial abelian monoid or whatever decoration you want. Okay. So the claim is that loop spaces are an example. So this is, if you remember from back in like the defining homotopy groups lecture, I think this like slide basically appeared. Maybe I made some minor edits. But what do? You so if you have a cube, so like what is this? It's like a cube. Yeah, we got this cube, and it's like crossed over S3 with functions. So I guess we're thinking of it. Maybe I should have written like each of these cubes is labeled by a function. So your cubes labeled by a function, what do? Well, you pick the function that's a scaled version. This cube is labeled by a function f1, which is a function from a cube to a cube, or a cube to x. So these fi's are functions from a cube to x that send the, so here we're thinking of loop space as functions from a cube that send the boundary to the base point. So you just use a scaled version of f in here, use scaled version of f2 in here, and everywhere outside of the cubes you go to the base point. So let's say we have v as a point in the cube. If v is in the image of some gi, so gi is going to be, our embedding from in into in. So we have like a k of these functions. So if v is in the image of one of them, so like, if v is this red point, then it's in the image of f2. And so you identify the red point with a point in the big cube using the embedding associated to this cube. And then you use the function to x. On the other hand, if your point is, not in one of these cubes, you just map it to the base point. And the functions will take the boundary of the cubes to the base point, so this construction is continuous. Yeah. So that's how loop spaces are CN algebras. Abelian monoids are CN algebras. So if you if you have cubes labeled by elements in an abelian group, you just add them all up. So we need cubes labeled by elements in an abelian group. We need a map to the abelian group. You just add them up. Here, maybe it's fine if A has topology. Like this will be continuous. Okay. If you have a monoid, you can do the same thing. If you as long as you have if you have a monoid, it's a 1 cubes algebra. So if you have cubes, 1 cubes in a 1 cube, so you have little intervals and a big interval, and they're labeled by elements of the monoid, you just multiply them. So like, why does this construction require, how come we can use abelian monoids when n is bigger than 1, but for n equals 1, we needed to, for abelian monoids, we needed n to, when n is at least 2, we needed to use abelian monoids. We could only use non-abelian monoids when n is 1. Like, why? What's the reason for that? Yeah, so like what would go wrong if A, B, and C were in a like non-abelian monoid with this definition? Yeah, you don't know.
Like how do you define the order if you don't know, like by the picture, how you get?
Yeah, the picture doesn't tell you the order, but in one dimension,
Yeah.
the picture does tell you the order. So so monoids give you C1 algebras, and abelian monoids give you CN algebras for all n. So this is part of the, like, CN algebras are like, as n gets bigger, are sort of more and more commutative up to homotopy. Okay, so there's a theorem of Peter, May, and Boardman-Bott. Boardman and Bott, that so the theorem that we're going to prove, and like this was proven first, says that if A is a connected CN algebra, then A is homotopy equivalent to a loop space. So here we had lots of examples of things that weren't loop spaces. Like this configuration space is definitely not homotopy equivalent to a loop space. It's related to loop spaces, but it's not, because for instance, like the connected components of loop spaces are all homotopy equivalent, and in configuration space, like if you have the configuration space of 1 point, it's contractible, but the configuration space of 2 points has the homotopy type of RPN minus 1, for example. So this is definitely not a loop space. On the other hand, this is not connected because the connected components are given by how many points you have. Yeah, so there's this theorem of Boardman-Bott that says that if you're a CN algebra and you're connected, then you have to be a loop space. So there's some improvements. So one improvement is that this connected can be improved to just having pi 0 a group. So if you're a CN algebra, pi 0 gets a natural monoid structure that happens to be abelian when n is at least 2. So pi 0 is naturally a monoid. Pi 0 of a space in general isn't a monoid, but pi 0 of a CN algebra is naturally a monoid. And if you assume that pi 0 of A is a group, that's enough to make, you can replace the assumption that it's connected with that pi 0 is a group. So you should think of pi 0 being connected as like it sounds like a points set topological condition. We should really think of it as an algebraic condition. It's the statement that if pi 0 is connected, then it has a single element, so it's like it's the 0 monoid or the 1 monoid, whatever you want to call it. So it's a statement that the monoid happens to have inverses. Like if a monoid with 1 element is a group. That's what I'm saying. If M is a monoid with 1 element, then M is a group. Why? Well, that 1 element, we just need to find inverses for everything. The 1 element is an inverse for itself. Great. So that's one improvement. We're not going to prove it because it's slightly easier to prove it using the assumption that A is connected. It's not necessary, but it streamlines the proof, and historically was the first version proven. And then the second improvement is you might want to say, like, hey, A is a CN algebra, loops NX is a CN algebra. And you might want to know that sort of they're equivalent as CN algebras. So what we're going to do is we're going to find some CN algebra A prime that maps to both of them. And these maps are going to be homotopy equivalences and maps of CN algebras. So this is basically going to say, like, not only this type of thing is called a zigzag. So like, not only is it a homotopy equivalent to a loop space, the homotopy equivalence basically respects the algebraic structure.